In this video, we're going to go through how an acid HX adds to the double bond, the alkene, and talk about Markovnikov addition. Okay, so if I have an alkene, double bond, and I react it with HBr, in this case, I'll draw that out. What you're going to get is addition to the double bond of the HBr. So the hydrogen will add to one of the carbons and the bromine will add to the other carbon. And if you look at this, the bond that we're breaking is the double bond. That's different. And the bonds that are being formed are the carbon-hydrogen bond and the carbon-bromine bond. And how that happens mechanistically, the double bond is the nucleophile. It can attack. It has the extra electrons. And this is the hydrogen is the electrophile. Right, so that's the one that gets attacked. And what I wind up doing is taking the two electrons from the double bond, creating the bond between the hydrogen, and breaking that bond. Also, I forgot to mention that this bond is broken as well. Okay, so what happens when we do that? Those two electrons go to form the carbon-hydrogen bond. This is the new bond being formed here. And that leaves behind a plus charge because I've taken the electrons away. I've also generated a Br minus in the process when the HBr bond breaks. And now what happens is the bromine is the nucleophile. It attacks the positive electrophile. And what I wind up with is formation of the carbon-bromine bond as part of the second step. So I have addition of H plus, right? I form a secondary carbocation, right? It's got two alkyl groups attached to it. That makes it a secondary. And then attack of the bromine. Br minus to form that bond. All right, so this is great. And in this example, I've drawn a symmetric double bond. So either side that it adds to, because of the symmetry, I have a CH3 here and I have a CH3 here, hydrogen here and a hydrogen here. I have a symmetric double bond, so it doesn't matter what side it adds to. One side gets the hydrogen, one side gets the bromine, and it really doesn't matter. But what if we don't have a symmetric alkene? What happens then? Okay, so let's look at an example of that. So let's look at this one, and we're going to react it with HBr. So we know these are the bonds that break. And I know I form bonds between a carbon and the hydrogen and a bond between the carbon and the bromine. And what I'm going to do is I'm just going to draw out both of those possibilities. So the first possibility is going to be if the hydrogen adds to this side and the bromine adds to this side. And the other option is going to be the hydrogen will add to this side and the bromine will add to this side. And I want to figure out which one is which. So the way to do that is we need to explore the mechanism. So what I'm going to do is I'm going to take this alkene and split, adding of hydrogen to one side. I'll do that in one color. I'll do this first one in red. And the other one I'll do in blue. We'll have it add to the other side. And I'll generate a separate arrow for that. So this is going to be the first way we do it. And in blue will be the second way that we do that addition. All right, so let's see what happens. So the first one, right? I add the HBr to this side. I wind up with a carbocation. Again, this is a secondary carbocation. Let's look at the other possibility. It could add to this side, right? Remember, this is 1. This is 2. And what I'm going to get when that happens is I'll create the carbon-hydrogen bond, and I'll get the cation on this side where I took electrons away from it. And this would be a primary carbocation. So carbocations are electron deficient. The more carbon atoms I have, or atoms that could add electrons to it through an inductive effect, the more stable it's going to be. So I could see right away that the secondary carbocation is going to be the most stable, right? And that's really what Markovnikov addition is. We add to the double bond in a way to generate the lowest energy intermediate. The primary carbocation is high energy or higher energy, and this would be lower energy. And that's the way that it forms. So we're going to generate this carbocation, and I'll redraw it over here without all the nonsense attached to it. And then the Br minus is going to attack, and we're going to generate this product, and this product will not be formed in that reaction. Okay, so remember Markovnikov addition. One way you could look at it in a simple case is how many hydrogens are on the original double bond. Let's look at this. So let's just draw out every hydrogen. And this is the way I learned Markovnikov addition at first, before I took any advanced class. The side with the most hydrogens gets the hydrogen. So this has 2 hydrogens, this double bond. This side of the double bond, this has 1 hydrogen, this side of the double bond. So the H plus is going to go towards the side that has the most hydrogens. And what that really does is it gives you the most stable or lower energy carbocation. Right, and that's really the point of all this. All right, let's look at some other examples where other things could happen. Okay, so let's look at maybe a little bit more substituted of a molecule here, and I'm going to react this with HBr. And what I'm going to do is I'm going to go through this mechanistically, and we're going to see what happens. We're going to follow Markovnikov addition. Right? We're going to add the hydrogen to the side with the most hydrogens, and what that does is it generates the most stable carbocation. So the hydrogen will add on this side, and I'll get a plus charge here, and this is a secondary carbocation. But there's another lower energy alternative. If I could move this hydrogen over and do a 1,2 hydride shift, what happens is I generate a different carbocation intermediate. And now this is a tertiary carbocation. Remember, carbocations are electron deficient. The more alkyl groups I have donating electrons in, the more stable. So this is more stable, and this is less stable. That's why the 1,2 shift happens. And then the Br minus that I've generated in all this is going to attack that carbocation. And the product I'm going to get is this one. Okay, so now if we look at what's going on here, obviously I've broken this bond, I've broken this bond, but I've also broken the bond here to shift the hydrogen over. And the bonds formed in this case are going to be this bromine bond, this hydrogen bond, as well as this hydrogen bond. Okay, so that's with the 1,2 hydride shift. We could also have a 1,2 alkyl shift. That could happen to generate a more stable carbocation. So I'll draw an example of that over here. Now let's have some more methyl groups on this side. And I'm going to react this with HBr. And I want to know what the products are going to be from this. So I'm going to do my standard Markovnikov addition, make the more stable carbocation. That'll give me this intermediate plus the Br minus that I generate from breaking that bond. Okay, so this is a secondary carbocation. And if you remember from Organic 1, if a cation could rearrange to make a more stable carbocation, it will. So if I do a 1,2 alkyl shift, so I'm going to move one of those methyl groups over. What I'm going to generate when I do that is a tertiary carbocation. Right. So I've shifted over the methyl group, made a tertiary carbocation, which is more stable. Because of the groups that are attached to it. And then my Br minus will react here, and I'll wind up forming the product of that addition. Okay, and let's look at what's going on here. The bonds that we've broken are the double bond, and the methyl group has shifted over. The HBr has also been broken, and I formed the carbon-bromine bond. I formed this carbon-carbon bond, and I formed this carbon-hydrogen bond. And that's it. Remember, to summarize, we're trying to make the most stable carbocation. That's essentially what Markovnikov addition is. Once I generate that carbocation, I have to look for possible rearrangements that could occur to make an even more stable carbocation. And then the bromine will react in it too.